but
Stop talking.
nothing's coming up. I don't know if this is the same.
Oh no, it's different.
Okay. How are we going to get it to everyone?
I'll share it in the chat.
Oh, that's smart. Okay, I'm going to just close that. And then where's Zoom chat? Stop sharing because I can't find the chat. There we go. Okay.
Thank you.
Thank you.
Awesome. I'm going to mute myself.
Okay.
Good luck.
Thank you. Okay. I'm going to add my video now. Okay.
The chat is shut.
Oh, in YouTube?
Yeah, in YouTube.
I think you can log into that as well, right?
Yeah, but because the lecture isn't live, because you ended the scheduled one, it's disabled. The chat's disabled.
Okay, that's okay. People can just go on Slido, I think.
Yeah, I might send out a mass email with the new link as well.
Okay.
Okay.
And you've got the new link.
Yeah, I might send out a mass email with the new link as well.
Okay.
I
The
think
link is unlisted, July, so you're going to have to make it public. You're muted as well. July?
yep. Here. So, edit.
Nothing at the moment, baby.
Okay. I just made a public.
Perfect.
Okay.
I'm going to put the new link in the old.
Oh, that worked. I think.
I'm going to put the new link in the old description, so people should go there.
Okay.
So we'll wait for a little bit until we've got some people, and then you can go.
All right.
Awesome.
Thanks. Hi everyone who's on Slido. Are you able to hear and see me now? Okay, there's 8 people watching the stream. All right. Hi, everyone. I think I've got most of the technical things sorted. I'm very, very sorry about the kerfuffle and having to send out a new link as well. In order for everybody to join us here today, we're going to wait until 2:15 before we start. This is some extra 5 minutes for the people who are able to join back on with us before then. Feel free to ask questions on YouTube or in Slido, and we can have a little conversation while we wait for everybody to join us again. Ah, right. Yes, Christina said, "Hooray! I thought it was a problem at my end. I'm very sorry. I would for this. Thank you so much for joining again." Yes, Clive also said the same thing. Definitely not any of your fault. I accidentally closed the scheduled live stream, which is why we have a new link here today. Osgrab, Arc Center of Excellence, excited to hear your talk. Thank you very much. Hopefully we can get started and I don't accidentally close something once we get started at 2:15 AEST. Rudra says hi. Hello. It's very strange giving a talk over the computer. Normally you're all in the same room with me, but now all I can see are people writing in messages. So I really appreciate all the hellos and shout outs on YouTube that I'm seeing. Yes, for those of you who are at home and watching on YouTube, I've enabled the chat function on YouTube. So now if you refresh the page, you should be able to type in comments and questions. Thank you, Rudra, for bringing that up. I see some new questions on Slido. Someone asked how long this session will be. The talk itself will be about 40 minutes, so you should be able to listen to all of it within the hour. However, we will have some time afterwards for questions as well for those who can stay. Why and how do stars look so pretty when they explode? They do look very pretty. And I'll talk a little bit about stellar explosions today, but we can definitely chat more about that after. Does anyone know exactly when the sun will explode? This is a very good question. Something that luckily humans that are alive right now don't have to worry about. It should be in about 5 billion years. The code for Slido is Astro. So if you go to slido.com and enter this code here, Astro. We've got people on YouTube answering each other's questions. Thank you very much. So it is 2:15 now, and it looks like we've got 94 people who have joined, and I'll make a start so that those of you who need to leave on the hour can hear the whole talk. All right, you've been listening to me speak for a while now, but let me introduce myself a little bit. Hi everyone, my name is Jielai Zhang, and I'm an astronomer. My favorite thing about research is finding ways and techniques to see the universe in a whole different new light so that we can understand it more and discover new things. And this is really exciting. So I'm joining here today with you on YouTube Live, as you all know now, and you've seen that I've made some kerfuffles, and it is something quite new for me, and I've never done this before. So to make this talk interactive, you can all join at slido.com and enter the code ASTRO, or you can in fact just take your phone and point it at the QR code with your camera, and that will allow you to get a link to go to slido.com where you can ask questions as well as join in on the interactive parts of this talk. I'm speaking to you today from the traditional lands of the Aurora Nation. I'd like to acknowledge that the traditional custodians' land on which I work and live, and I recognize their continuing connection to the land, water, and community. I pay my respects to the elders past, present, but also emerging. I'm joining you all today, and you're all in your respective houses, so it's very hard for me to get a sense of where you are and what you're all doing. So the first 3 questions I've got for you today is about you. Would you be able to tell me what time it is over there? If you're on slido.com, the question should pop up for you. I've got 3 responses now, 4 responses. This is good. This is a good time zone for most of you. Somebody is joining in the morning, 6 a.m. to noon, midnight to 6 a.m. Wow, we've got somebody joining in the middle of the night. Welcome, and thank you for joining us today. I'm glad most of you are, it's a reasonable time. For those of you joining in the very early hours of the day, thank you so much, and I hope I can make this fun for you. I'll wait till this goes up a little bit more. There's actually a few people joining us between midnight and 6 a.m. Wow, thank you. All right, I'll move on to the next question. How old are you? All right. People are getting faster at answering these. This is great. If you have any questions about how to interact with us today, you can post them on YouTube or post them in Slido as well. We've got a lot of people who are between 30 to 50 and also 50 to 70. 12 to 18. Oh, a few people younger than 12 and older than 70. Well, welcome to all of you. It's so exciting to see such a wide range of ages joining with us today. Hopefully my talk will be able to be applicable for a wide audience. All right, my last question for the audience is, can you please tell me one word that explains why you are joining us today? If you make it one word, it will allow a word cloud to be made and therefore get a sense if different people have similar reasons to join us today. Astronomy, sunshine, curiosity seems to be a really big one. Friend, oh, okay, I guess you're my friend and you're joining me to support me, thank you. Curiosity is really big. Astronomy, science, learning, that's really, really good. I hope you learn interesting and exciting things today. Friend, science. Isn't this word cloud thing cool? Lockdown, yes, we are definitely in lockdown in many places around the world today. This is a very good point. I hope all of you and your families and loved ones are staying safe. Osgrav, intriguing, fascination. Curiosity is a really, really big one. I can share with you that the reason why I decided to do research and be an astronomer is because of curiosity. Space is just so beautiful and wonderful, and I hope you'll learn something that's unexpected today. So let me now go on with the talk. As we look up at the night sky, this is the reason why we're all here today. It's absolutely spectacular. So you can see here a photo of the Milky Way galaxy, which is this band of milky material and stars across the sky. Us as humans live on planet Earth, and the Earth goes around the sun, and the sun is a star in the Milky Way galaxy. So the Milky Way galaxy is like a pizza. It's a disk, and we're in it and looking through. So what we see is this line of stars across the sky. You can see in this picture something really cool. Off to the side, there's this little fluffy cloud thing. That is actually a nearby small galaxy called the Small Magellanic Clouds. When we look up at the night sky, it looks the same from night to night. So this photo here would be what people would see 1,000, 2,000, 5,000 years ago. In fact, the stars and the sky is so constant that we can use it to navigate the oceans, the same way we did 5,000 years ago as we do today. The stars' brightnesses are the same, and their relative positions are the same as well. Of course, today you might use GPS to navigate the oceans, but if you did not have a GPS, you can use the stars. For example, there's a constellation you can see in Australia and the Southern Hemisphere called the Southern Cross. And the Southern Cross can allow you to find out where south is. So if you take the long edge of the Southern Cross and draw a line, find these two bright stars nearby, and then draw a line to cut it in half. Where these two lines you have drawn meet, you point it down, that is the direction of south. This is a really neat trick, and if you do a little bit of practice, it's very reliable. So next time you go out with a friend at nighttime, you can tell them what direction south is. They can check on their phone using the phone compass and be like, wow, you're amazing. You can figure out south without your phone. Not only are the brightnesses and positions of stars constant throughout time, even the dark patches in the Milky Way remain the same as well. And so some constellations are not made up of stars, and they can be made up of these dark patches. An Australian Aboriginal constellation is the Emu, and I've attempted to draw the shape of this Emu constellation. An emu is an Australian animal that looks like this. They are very intense. Do not approach or interact with them. They can peck you really hard, and that's very dangerous. But they're very cool. So these constellations remain the same over time. I now have a question for all of you again. I've talked a lot about how constellations and stars remain the same over thousands of years, over human history. What are some objects in the sky that you know of that do change noticeably in less than 10 years? Maybe over days, weeks, or months, or a year or so. This time you can enter more than one submission, but please only enter one object at a time so that we can create a nice word cloud. Any types of objects in the sky that change in position, in brightness, or the way they look. We've got answers coming in. This is very exciting. Planets, FRBs, comets, the sun, variable stars, pulsars, Jupiter, red spot disappears. Planets is a really big one. So planets were discovered quite a long time ago. I can't remember exactly when. And the word planet in some language, maybe Greek, I'm not 100% sure, actually means moving star. And so it was these dots of light in the sky that did not remain in the same position over time. So that's definitely one of the very first types of changing objects we saw in the sky. There's comets, moon. Yes, the moon looks different from night to night. And that's because of the shadow That's because of the light not illuminating the whole moon, which we can talk about after if you're interested about the phases of the moon. We've got another big one here, supernova. Supernovas are very exciting, and so that's what I'm going to talk a little bit about now. And I'll move on to the next question now, to move on with the talk now. So together with planets and the changing phases of the moon and the different ways that planets look over time, such as Jupiter, one very exciting transient object that makes the sky look different from time to time are called supernova. And in fact, supernova have been known about since for over 1,000 years. In 1054, there was a supernova that went off that was really, really bright, and it was recorded in the history books of many different places, including China and Japan. The supernova, in the position of the supernova, there was nothing. And then suddenly, one day, someone woke up and saw this bright star in the sky. It was so bright, it's brighter than the moon, and you can actually see it in the daytime. It's very strange to see stars in the daytime because usually we don't see stars. The reason we don't see stars is not because they're not there. You look in the sky in that direction, the star is still there. You just can't see it because the sun is so bright. It's kind of like if you're walking around at nighttime and you can see if someone's sitting in a car on their phone, you can see their phone, right? But if they flash their floodlights at you, then you can no longer see the phone because the floodlights are so bright it blocks and obscures the existence of the phone. So this supernova was so bright, it was visible in the daytime sky for over 3 weeks. And even after that, it was visible in the nighttime sky for over 2 years. So we've known about some transient objects for a very long time. What I want to talk to you about today is that other than supernovas, we didn't know about anything that changed in the sky for centuries until 3 recent discoveries. And these 3 recent discoveries completely changed our view of the universe and the kinds of activity that can go on and how fast these activities can occur. The first discovery was made serendipitously, so it was made by chance. And it was made by people who were not even trying to study the cosmos. In the 1960s, the US and the USSR, which is what Russia used to be called, they were in a Cold War. It means they were competing with each other to build the best technology, come up with the best science, and show who is the best and strongest. However, when they invented nuclear weapons in the 1960s, they decided nuclear weapons should not be messed with, and they decided to sign a treaty to say we are not allowed to test nuclear weapons. Even though this treaty was signed, the US did not just want to trust that Russia was going to abide by a signed piece of paper. And so the US launched a series of satellites called the Vela satellites. Vela means watch in Spanish. These satellites were launched into space to catch the signatures of nuclear weapon tests so that they can see if Russia was actually abiding by the treaty or not. These satellites that go into space cannot tell what direction the signature of the nuclear activity is coming from. But if you launch several satellites into space, then if they all observe some nuclear testing activity, the timing of when they detected that activity can tell you the location of the nuclear test site. So this way, the US can be like, hey, some nuclear test activity went off, and figure out where it is, go check it out, find out what's going on, and then go up to Russia and say, hey, you said you won't test, now you're testing, what are we gonna do about it? Something that's really cool though is while they're detecting these nuclear tests, before I say that, what signatures are there to detect for nuclear bomb testing? So the nuclear bomb testing, these are very energetic, super energetic activities, and that comes with releasing very energetic types of light. You're all very familiar with visible light, which is the light that we can see with our eyes. This light, but actually there's a whole range of different types of light that's both more and less energetic. For example, the sun releases UV light, which can cause cancer. There's X-ray light that allows you to image bones, and there's gamma radiation or gamma rays. You might have heard about this in superhero movies, gamma ray, thunder, lightning storm, and suddenly you have superpowers. The superpower part is fake, but gamma rays do exist. And the lower energy end, there's also infrared radiation, which is used in TV remotes, and radio waves, which is used to listen to the radio. That's before everybody started listening to the radio via the internet, of course. So these nuclear bomb testing will release the most energetic types of light, this gamma rays and X-rays. And the Vela satellites are designed to be able to measure X-rays and gamma rays. But in 1969, some strange things were detected. They observed some gamma rays, but they were not coming from anywhere on Earth. They were not even coming from the sun. Sometimes when the sun flares and they can release some gamma rays. But this gamma radiation was not coming from the Earth, not coming from the sun, and it was a burst. Some of them were less than a second, and some of them were up to 30 seconds. They were named gamma ray bursts because it was a burst of light and then it disappears. This was this was published in 1972. It wasn't until 1997, approximately 30 years later, that we found out just a little bit more about these gamma ray bursts. It was really hard to figure out what they are because they would burst, disappear, and then you have no trace of it to follow up and then study it further and find out what it is. But 30 years later, people designed these telescopes that was able to find a lot of gamma ray bursts. And what they found was these gamma ray bursts were going off in every direction in the sky. It wasn't concentrated to the band of light that is the Milky Way. So it was coming from everywhere in the sky from beyond the Milky Way galaxy. These dramatic bursts of light that last a second or up to 30 seconds. My cat just jumped on. She says hi. Sorry about that. This was very exciting. For the very first time ever, the universe became something that can change within a second. Something can go bang in a second. And for 1,000 years, we only knew that the sky was constant, or the supernova can go off and brighten and dim over days and weeks. The second discovery that I want to tell you today is also made serendipitously. This discovery was made by astronomers, though, in this case, and not people involved in politics. Astronomers were trying to study these objects called pulsars. Pulsars are dead stars. I'm going to just put her out of the room. 1 second. Sorry about that. Pulsars are dead stars, and they have very strong magnetic fields, and they can spin up to 1,000 or more times every second. The strong magnetic fields cause these radiation to come out in 2 jets on either end. And as the pulsar spins, this radio light will spin in and out of the direction of Earth, just like a lighthouse. So what we see are flashes of radio light up to 1,000 or more times a second. And these were being studied by astronomers to understand dead stars. Something that's very cool about radio light happens. There's a cool thing with radio light when it travels through material in the universe. So a pulsar emits radio light at some radio light is shorter frequencies, and some radio light is at longer frequencies, and they all travel through space uniformly. However, when this radio light goes through some medium, something interesting happens. And I'm going to show you a video to demonstrate this. So we've got the light traveling together, And now it goes through some material. And as it goes through this material, the shorter wavelength light is actually able to travel faster than the longer wavelength light. And so it starts to race ahead. And the more material that it travels through, the faster, the more raced ahead the shorter wavelength light is. For these dead pulsar stars in the universe, the time delay between the arrival time of this shorter wavelength and the longer wavelength is not huge. It's about up to or around a millisecond. And so astronomers were studying these pulsars when they found a very strange signal. This is a scientific plot, so let me explain it a little bit. This is a signal they found. They found a giant pulse of radio light where on the x-axis here you've got time, so this is 0, and here you've got 500 milliseconds, which is half a second. And on the y-axis, it's frequency. This is a higher frequency and a shorter wavelength. And this is a larger frequency and a longer wavelength. So you can see the longer wavelength light of this signal arrived later than this shorter wavelength light. But the interesting thing is that the delay time between the longer and the shorter wavelength light was almost half a second. Remember these pulsars that astronomers are studying? The delay time is about 0.001 second. And here it's 0.5 seconds. Not only that, pulsars will emit these pulses of light up to 1,000 or more times a second, but this was a single pulse of light that seems to be coming from something that's potentially very far away because it had to travel through so much material to get to us. I'm now going to ask you another question. But before I ask you that question, which is about how far you think this burst of radio light is coming to us from, I'm going to show you a video to give you a sense of different lengths in the universe. So we're starting with a proton, and it's very, very small. You can see the decimal point here, many, many decimal points small. It's DNA. We're up to ants and pennies. And now there's no more decimal points, so we're in the meters now. This is very America focused. And now we're starting to look at sizes of things in our solar system. You can see how that's a lot of zeros. I see that I've spurred a conversation on YouTube about cats. In the YouTube video, CASPublicLectures is answering questions. Shout out to Sarah Webb, and Simon Good, who are graduate students at Swinburne University who are helping me answer questions. So that is the Milky Way galaxy, and our nearby large galaxy is called Andromeda. And if we zoom out even more, you can see there's galaxies around us, including the Small Magellanic Cloud would be in that spot there. Galaxies are clustered into clusters of galaxies, and then those are clustered into superclusters of galaxies. And on the larger scales, we have the observable universe. All right, so now you have a little sense of what are the different scales in the universe. I have a question for you. This burst of radio light that was observed with a half-a-second time delay in arrival time of the shorter and longer wavelength light, that was named a Lorimer burst, named after the person who discovered it. I have a question for you, which is, how far away do you think this is, this crazy thing which had a 0.5-second delay time, a delay arrival time? This is a guess, just to see what you all think about how far it might be. You're not expected to know the answer. I had to figure it out too. All right, so it looks like most people are guessing beyond our Virgo supercluster, but there are also some people that think it might be within, or maybe it's in the solar system, and we all got tricked. All right, I'll stop this here. It turns out that most of you are correct. This Lorimer burst, based on the amount of material that the light had to go through in order to make such a large time delay between the longer and shorter wavelength, that meant this was coming from somewhere beyond the Virgo supercluster. This was discovered in 2007, but for the next, and astronomers who found this continue to study this location, but they never saw another burst, even though they observed it for many, many hours. It wasn't until 2010 that that other bursts like this that looked similar were found. But something very strange was going on with the bursts that were found in 2010. So this object that's supposed to be really, really far away, if it's so far away, it should be a tiny little dot in the sky. And so when our telescope points, we should only see it in one single direction. But the bursts that were found in 2010, and there were a whole bunch of them, if you point the telescope all around, you can see it. It's coming. This light was coming from all sorts of directions and not just the one in the sky. This kind of signal hinted that the source is not from space, and instead it's coming from Earth. And so this was a big hit and shock to people who studied and learned about the Lorimer burst, because suddenly it made the Lorimer burst seem suspicious. I watched a talk online once by Lorimer himself, and he told us a story. Soon after the discovery of these bursts in 2010 that seemed like the source was on Earth, he went to a conference, and a speaker at the conference asked the audience, do they still think the Lorimer burst was a real cosmic signal? Lorimer was sitting in the front row, and he said he did put his hand up. He still believed the Lorimer burst was real, but he was too scared to turn around and see if anybody else had put up their hand. It wasn't until 2012 that another signal like this was found. And this time, this signal did come from a single location in the sky, confirming that the Lorimer burst is probably something real. Around that time, these bursts became named fast radio bursts, a fast flash of light in the sky that lasts less than a second, a burst that then disappeared afterwards. I remember at the beginning when I was asking you a question in the word cloud, some of you did put FRB in there, so you already knew about this. This mystery of the signal coming from Earth, it wasn't until 2015 that Petrov figured out what was going on. It turns out these signals were coming from a microwave. If you open the microwave oven door before the timer runs out, it creates a signal. And part of the clue why this was actually what was happening is that these signals bunched up around lunchtime. So Petrov was able to figure that out. And FRB, the story of FRBs completely took off. So now I've told you two amazing discoveries that were made serendipitously of how the universe and the sky changes on the timescale of seconds. We've got gamma rays, the most energetic type of light, going boom in the sky all over. And we've got fast radio bursts. Fast radio bursts, we still have no idea what they are. And up until last year, the number of theories of what fast radio bursts are outnumbered the number of actual observations of fast radio bursts. That has changed now. We've got many, many more observations of fast radio bursts. I've got one final story to tell you about a discovery that is actually very personal to me. And this is a discovery and observation of gravitational waves. During my PhD, I actually studied galaxies, and galaxies don't change very much in human lifespans. By very much, I mean they don't change at all. And but now I'm studying the transient universe, how the sky changes on timescales of seconds. And what motivated me was really this discovery. It all started in high school in physics class. One day, the teacher was telling us about how great scientists are and how difficult their work is. And my teacher, she gave me the example of people trying to detect gravitational waves. And she told me and the rest of the class, but it felt like she was just speaking to me. She told us that scientists have been trying to detect gravitational waves for 40 years. And this is something that was predicted by Einstein 100 years ago, but they haven't been able to find this yet. This is an example to show how hard you have to look and how hard you have to try in science to make discoveries. So this discovery is totally the opposite of the discovery of fast radio bursts and gamma ray bursts because it was meditated. It took a lot of effort. It took whole careers of people. And so to me, the detection of gravitational waves was the holy grail of the persistence in the pursuit of science. In 2016, gravitational waves were discovered for the first time. And I thought, wow, we did it. By we, I mean, obviously I didn't do anything, but as a human race, we did it. We detected gravitational waves. And it was done by scientists who, they spent their whole career on it. And until it was detected, they didn't even know if the thing they spent their whole entire life on was going to result in any detection at all. It's just very inspiring to me. How do you detect a gravitational wave? Well, a gravitational wave is the warping of space-time itself. And you can notice this. If a gravitational wave were to come across in this direction and go through my arm, then the length of my arm would shrink and grow and shrink and grow until the wave passes through. This is a very difficult thing to measure because any gravitational wave will change the length of my arm by such a small amount that it's completely not noticeable to me or anyone in the universe. What makes a gravitational wave? Well, gravitational waves are made by a mass that moves through space. So right now, as I'm doing this whoop whoop action, my hand is creating a gravitational wave, but it's so small and imperceptible that nobody in the universe will ever notice. But in the universe, we have very, very massive objects that are moving and accelerating around very quickly, such as maybe black holes. And these should give off gravitational waves that might be detectable on Earth. Not by my arm, of course, but by gravitational wave detectors. So here is the picture of a, oh, you noticed. Thank you, Scott. I think Scott means they noticed my arm moving around. Thanks. Anyway, so gravitational wave detectors are made up of two arms, and they are built so that the lengths of the two arms of these detectors are exactly the same. In this case, it's 4 kilometers long each. The actual absolute length of these arms is not, if the change in their length as a gravitational wave goes through would not be measurable because it's too small. We just wouldn't notice. But we do have a way to measure the difference between the length of these two arms. And so if a gravitational wave were to come through this way, it would shrink and grow this length compared to this length. And therefore we would make a detection in this building over here. Just like the Vela satellites, these gravitational wave detectors cannot tell what direction the gravitational wave came from. However, if you have many of these gravitational wave detectors, then you can figure out the direction from which it's coming by looking at the timing of when the signal arrived at the different detectors, just like the Vela satellites. All right, so here is the discovery in 2016. This panel here, the second panel here, is the data that was observed at the gravitational wave detector. This is a model or a simulation of what this data could be of. And here in the bottom panel is the model minus the data. This is to have a look at how similar the model and the data is. On the x-axis is time. And so from here to here, the signal only lasted 0.2 seconds. And on the y-axis is the difference in length of the two detector arms over time. In the top panel here, it shows you physically what was happening. And we could tell this based on modeling the data. So what was detected in 2016 are two black holes that were orbiting each other, and then they spiraled in towards each other and eventually merged and became one single black hole. This was an absolutely phenomenal discovery. Not only was this the detection of gravitational waves for the very first time ever by scientists who've been working on this for 40 years, it was also the first direct detection of black holes. It was also the first ever confirmation that binary black holes that orbit each other actually existed. I remember the week that this news came out, I was walking down the corridor in Toronto where I did my PhD, and a friend was walking towards me, running towards me, very excited to tell me something. And he said, "Guess what? The thing that I've been doing my whole PhD on, I now know that it actually exists." So my friend worked on binary black holes, and many people had been studying these for a long time, even though we didn't know if they really existed or not. Because we've never made a detection before. This was really, really exciting. The energy that's released by the two black holes merging together to make one, this energy was released within 0.2 seconds. And the amount of energy, if you convert it to visible light, is equivalent to the amount of light released by 10,000 Milky Way galaxies. But instead of this energy coming from 10,000 Milky Way galaxies, it came from two black holes. This is absolutely amazing. So I wanted to ask you a question. I've been talking on and on about how difficult it is to make the measurement in the length difference of these gravitational wave detectors. So what do you think was actually the measured length difference? Thickness of a hair. This is tiny. Imagine trying to measure the difference measure a length that's the thickness of a hair over 4 kilometers. Got less than the size of an atom. Can you even do that? That's crazy. Size of an atom, So most people are saying it's less than the size of an atom. I'll wait till this number goes up a little bit more. Thickness of a hair. Less than the size of an atom is winning again. Got lots of responses coming through on YouTube as well. Hair, less than an atom. Thickness of hair, less than the size of an atom. So it looks like we're fighting between around these two answers. We've got 42 responses now, so I'm going to reveal the answer. The answer is the measured difference in length was less than the size of an atom. Before I learned about gravitational wave detectors, I did not even think this was possible. I mean, like the equipment you use to measure distances, like how can you even tell it's less than the size of an atom if all the equipment is made up of atoms? And so this is just points to how incredibly phenomenal and sensitive gravitational wave detectors had to be in order to even make a detection of gravitational waves. They're so sensitive that if a wave crashes upon a beach shore miles away, this detector is capable of detecting that. All right, so I've told you about 3 recent discoveries that completely changed our view of the universe. Before these 3 discoveries, we thought the universe was tranquil and it didn't change from year to year or even century to century. But with these 3 discoveries, we realize that the tranquility of the night is just a disguise to tickle the curious. At the beginning of the talk today, many of you said that you were here because you were curious. I hope that your curiosity is a little bit satiated, but also completely grown, because suddenly there are these sources and flashes and bangs in the night, releasing energy as much as 10,000 times the energy from a whole galaxy within a second, going off all the time. And some of them, we don't even know what they are. For example, fast radio bursts. And so the quest is on to be able to study these objects in all the wavelength so we can find out what they are. So for example, fast radio bursts, we've only detected signals from them in radio waves. But if we can see them in invisible light or gamma rays as well, then we can really start to understand what actually did it. The reason why we want to study all of these at different wavelengths is because they all reveal different types of information. It's kind of like if you have a heartache, you'd want to go to the doctor and they'll listen to it with a stethoscope, or you can get an ECG, but getting an MRI would give you even more information and tell you things that a stethoscope would not be able to tell you. This is a picture of the Crab Nebula. This is what remained in that location after supernova 1054, the one that Chinese astronomers recorded in their books found. This is what remains. And you can see that using different wavelength light, the Crab Nebula looks completely different. And so astronomers have a lot of work cut out for them. We really want to observe as many of these events as possible and to point as many telescopes of different wavelengths to study them as possible. But this is really hard because, you know, an FRB, a fast radio burst, it goes off, it disappears within a few seconds. So unless you can get telescopes on it within seconds, minutes, or very, very quickly, you're not going to catch any other light. I've got one final question for all of you, and I'm not going to show your answers because it will take too long, but if you had to get information about a burst that you just discovered to others as quickly as possible, how would you do this? Give me some ideas, and maybe you can help the progress in understanding the fastest bursts in the universe. I'm trying to see. Bring the cat back. So I'm not sure, again, I have a technical difficulty. I'm not sure how I can see if people are putting the answers in, but I'll just leave this up for you to pop in your answers. And if you can't into this question, then feel free to offer me suggestions, ideas in YouTube or in Slido's question and answer as well. All right, so that brings me to the end of my talk. I hope you are excited about the state of the transient universe, as excited as me, because these 3 discoveries that I told you about, they've completely changed our view of the crazy stuff that goes on in the universe. So now I will take questions. Sarah and Simon are going to send me questions on my phone. So let me have a look at what question they've picked out for me. When will Betelgeuse explode? So this is a question from the audience. Betelgeuse is a star that have been undergoing a lot of activity recently. Instead of steady light coming from it, the brightness of it is fluctuating wildly. I can't give you a very informed answer of exactly when it might explode. Firstly, nobody knows, and it's very hard to predict. However, I can't even remember off the top of my head what are the possible ranges. And so what I can do is I will look this up and post the answer on the YouTube link. But if you want to, you can also ask me on Twitter. You should be able to see my Twitter account to the left of the screen. And I will give you a more informed answer because I don't want to say something that's not true. And Betelgeuse is very exciting, so actually there's probably a lot I can say. I'll just have a read about it and post to you a better answer. The next question is, what imparts spin to solar, star systems, galaxies, etc.? What imparts spin to solar? Oh, that's the same question. So this question might have come up because when I was talking about pulsars, and I said it can spin up to 1,000 or more times a second. What is making all this stuff spin? Like, the universe looks so peaceful. Why is everyone spinning so fast? Well, stars and galaxies, they form over time, and they form out of the material in space. This material, even at the beginning of the universe, at the time of the Big Bang, is not completely stationary. It was a hot plasma, and everything was moving around. As the material collect together, if these material had a slight tendency to more of them were moving in one direction than the other, as it collapses, it will spin up whatever object it is that's formed, including stars or galaxies. And it will spin up faster and faster as the collapse happened. Have any of you gone on those those things in the playground where you spin around in a circle. Oh, no, ballerinas. Here's an example. You know how ballerinas are spinning and they have their arms out, and then when they pull their arms in, they start spinning faster? Or ice skaters. And that's because as things collapse, the original motion that was going around gets faster and faster as everything condenses together, because the energy has nowhere to go as the thing gets smaller. The next question, if for any of these questions, if you feel like I did not give an adequate answer, continue to ask on YouTube, or you can ask me on Twitter as well. The next question is, when the Milky Way collides with Andromeda, what will be the energy output in gravitational waves? This is a very, very interesting question, and I'm afraid I actually have no idea in terms of the galaxies themselves coming together. But what I can say is that the amount of gravitational wave that is released really depends on how you really need a large mass to move very, very quickly. And those kinds of speeds that's required are things like stars orbiting around each other, black holes orbiting around each other, and colliding. And when the Milky Way and Andromeda collide into each other, the number of stars that will actually smash into each other and the number of black holes that will smash into each other is actually very small. And so we will not suddenly see a whole lot of black hole and stellar collisions releasing gravitational waves that way. But in terms of just the effect of the bulk material coming together and how much gravitational wave that releases, I actually don't know. And maybe some people from Ozgrav will have a better idea and help me answer that on YouTube, because I don't even think I can find that on Google. So the next question, could the alteration in the orbit of a planet be used to detect gravitational waves? So let me answer the question this way. The Earth is a planet and it's going around the sun. And this is actually, the orbital motion of that is similar to the orbital motion of any stars or black holes that are orbiting each other. But the difference between the Earth orbiting the sun, or even if the Earth got nudged and the orbit of the Earth changed a little bit, is that the kinds of speeds the orbit is taking place is is too slow. You know those two black holes that collided into each other? They were spinning they were orbiting each other at 75 hertz, so 75 times per second. The Earth goes around the sun once every year, 365 days. And so it does release gravitational waves, but it's very, very small. Now, what about if the Earth were to collide into the sun somehow, if somebody came and nudged the Earth enough? Even then, the mass of the Earth is very small, and the mass of the sun is quite small compared to the two black holes. I forgot to mention that the two black holes that we first observed merge into each other, they were about 30 times the mass of the sun each. And so I think that, a nudge in the orbit of planets definitely would release gravitational waves, but it's very small and not able to be measured. Does anyone know exactly when the sun will explode? The sun is now about 5 billion years old, and it should live about 10 billion years. So we've got another 5 billion years or so more to go. Phew! How are black holes made? This is a really cool question. Black holes are the best. They're so strange. And the question how they are made is a really interesting one. There are for black holes that are the mass of stars, they can be made at the end of the life of a star. When a star is still living, it's giving out lots and lots of light. And the nuclear activity in the star is giving out so much energy that even though the star is very massive and there's a lot of gravity, which is trying to pull the star together, the energy released by nuclear activity is pushing the star and keeping it supported and keeping it from collapsing. However, at some point, the fuel of a star runs out. And when that happens, there is no longer the energy or the push outwards, and the mass of the star, because of gravity, starts to contract. At that point, if the star is massive enough and there is enough material, after some extra explodey things that can happen, which I think I will not talk about at length because it can take some time. Eventually, when there is no more pressure pushing everything outwards, if the mass of the star is large enough, then gravity overcomes all the forces that can keep things from getting on top of each other. For example, if you have electrons and you're trying to push electrons together, the electrons are negatively charged, and so you try to push them together. They're like, we're all negative, we don't like each other, and they don't want to get together. Similarly with protons, they're all positive. They're like, no, I don't want to get together, and so they will keep everything from collapsing. But there's a point where gravity is just so strong because it can keep it becomes stronger and stronger the more material you have. It can overcome all of these forces that push outwards, and the material just cannot be supported anymore, and it collapses. At that point, it becomes a black hole. Everything is on top of each other, and it's super dense. It's so dense that nothing can escape from it, including light. Do gravitational waves combine and superimpose like typical waves? I have yes. I'm going to say yes. If there are any Ozgraph people that think that I've totally got this wrong, please let me know. But gravitational waves, which is the warping of space-time, can be superimposed if two waves are traveling through the same space. Where are the intermediate black holes? That is, black holes hundreds of times the mass of the sun. This is a very good question, and part of the answer is came about via the detection of the gravitational wave signal, because for the longest time, the only way we knew how black holes could form were from these explosions of stars. And then after they explode, they can make a black hole if they're massive enough. But what about black holes that are more massive? It's not like there are black holes that... Oops, sorry, my phone just dropped. It's not like there are black holes. It's not like there are stars that's the mass of 100 or 200 times the mass of our sun. So where do black holes of those masses come from? Well, the detection of the binary black hole merging and becoming one black hole is one way these intermediate black holes can form. There was another question earlier which I can't find it anymore, but someone had asked, are there black holes at the center of galaxies? Yes. At the center of most large galaxies, astronomers are finding that there are black holes there, and these black holes are very, very massive. 1 billion or 100 billion times more massive than the mass of our sun. And so the question of where these black hole comes from is also an area of active research. But yeah. All right. So the next question is the expansion of the universe still accelerating or expanding at a steady velocity? This is a very technical question, so let me give a little bit of background on it. You know the supernova that we were talking about? Supernovas allow us to measure the expansion rate of the universe. Something that astronomers discovered is if you look at galaxies if you look at galaxies, they all seem to be moving away from us, other than the closest galaxies like Andromeda and the Small Magellanic Cloud. all the other galaxies, they're moving away from us. And the further away the galaxy is, the faster it is moving away from us. The interpretation of that, and if you're interested, ask me on Twitter and I'll show you some diagrams, is that the universe is expanding. And if the universe is expanding, then the space between every galaxy is getting bigger and bigger. And so between us and a galaxy, the space is getting bigger, so it looks like that galaxy is moving away from us. For galaxies that are further away, there's more space between us and the galaxy. So over the same amount of time, that space increases more. And so it looks like that galaxy is moving away from us faster. So we measured the expansion of the universe, and this was very surprising. But what was even more surprising is that it turns out the expansion of the universe is speeding up. And today, it is still accelerating. It is speeding up. The universe is expanding faster and faster. And that is all the questions that I have from Sarah. And we are 15 minutes past the hour. I can see that quite a number of people have left already because this event was supposed to go for an hour. I think for now we'll end the talk today. I am so happy that so many of you joined me and met my cat. It was really fun to talk to you about something that ignites my imagination and curiosity. And I hope that you go away today realizing even though the universe is beautiful and spectacular, it's also full of energetic explosions and bursts, which we don't even fully understand yet. Thank you very much. All right, bye everyone.